All right, here's the bell work. I will use point-intercept form on this one to solve. In fact, they already gave us a slope, and we do want to write this in slope-intercept form. So where it shows y equals mx plus b, we can already, right now, replace the slope with the slope they gave us as 11. But then to solve for b, we're going to use the x and y values from the ordered pair they gave us. 520, so x is 5, so I replace x with 5. And the y value is 20, so just replace the y value with 20. And then we're just solving for b, so 11 times 5 is 55. So now 20 equals 55, but plus b. And then subtract 55 from both sides to zero that part out, and then you've solved for b, which is all we really want. B then equals 20 minus 55 is negative 35. So then we end up with the equation y equals mx plus b. We know m is 11, that's the slope. And we just found the b at negative 35. And this would be the equation of a line that has the slope of 11 going through 520. So to get us started off though, we're going to look at some examples that we need to find, fix, and justify. Actually, we're only going to focus on finding the mistake, not so much fixing and justifying. The way we may do that in the process anyways. So in these first couple examples, like this first one here, it's 2 to the power of 6 equals 12. This is a common mistake. This one's more common than the rest of them that we'll see. But a common mistake that students make, they say, well, it's 2 times 6, which is 12. And no, that's not what this is saying. This is 2 to the power of 6, which is very different. That's 2 times 2 times 2 times 2 times 2 times 2. Which, if you actually calculated this, you'd see it's not 12. Is that 2, 4, 8, 16, 32, 64? So this would be 64, not 12. Okay, not 12. But it's important for you not to get those mixed up. An exponent is not indicating that we're multiplying the base by the exponent. It's not what that's saying. This one's less common on number 3 here. But if you had 2 to the power of 5, some students, from time to time, they'll say, well, you can change those out, right? You'd get the same answer. No, that's not true at all. 2 times 2 times 2 times 2 times 2 there. That's 2 to the power of 5. That'd be 32 if you put that in the calculator. And then 5 to the power of 2 is just 5 times 5, which is 25. Now, these don't look so different, but they're different enough to say they're not equal. So this would be like using the commutative property with multiplication. But it does not work with exponents and bases. Or on number 4, this doesn't happen too often, but 3 times x and x to the power of 3. These are, if we were to expand both of these, you'd end up with 2 very different answers. For example, 3 times x is 3 groups of x, meaning we're using addition. So that's x plus x plus x. Okay, so when it's expanded, we would use addition. But on the x to the power of 3, if we were to expand it, you'd still have 3 x's, but now the operation has changed to multiplication, which only in rare cases is the same, okay? And then this next one, it's negative 2 to the power of 3. You'll see if you were to expand the negative 2, especially using parentheses like this, that you'd have 3 negatives being multiplied. And we know that 3 is odd, which makes the answer a negative. So 2 times 2 times 2, though, is 8. So it just means you'd have to make that 8. Instead of positive, it would then be negative because there's 3 negatives being multiplied. All right, there's our objective. I know when to add and subtract exponents. So we'll take 30 seconds and copy that down, please. So this lesson is split up into 2 parts. We're going to look at when to add the exponents and also when to then subtract the exponents. So it's 2 different parts. We'll show you the rules here in a minute, but let's go over why this is the way that it is. All right, so again, this is for these 2 problems that I'm going to do right here. I'm going to expand them, and then I'm going to show you what they would be in then an unexpanded form or exponential form. But just understand that with these 2 problems, I'm going to be adding the exponents But now that I've told you that, I want you to think about why that works when I start to expand these, okay? All right, so I'm going to expand these. And I'm going to start with this 5 to the power of 3. I'll do this one in red, okay? So that would be 5 times 5 times 5. If I were to expand that exponent, expand the bases, okay? All right, now we are going to be multiplying this, which is shown with the multiplication here. So that's where that multiplication sign goes. And then I've got 5 to the power of 2, so that's 5, but 2 times multiplied, by the way. But we can see by expanding this that what we've done is we've created the same base being multiplied over and over and over. So now I have the same base being multiplied, but it's going to change that exponent. And how many 5s do we got? 1, 2, 3, 4, 5 of those, which makes our new exponent a 5 as well. So that's 5 to the power of 5. But like I said, this is where we would have taken the exponents and added them together. So really what we did right here is we said, hey, look, take this the base of 5 and the 2 exponents, which was 3 and 2. And yeah, as it turns out, you're just able to add those two together, which makes this property very convenient, okay? Because instead of having to expand these, which right now, where the numbers are relatively small, 3 and 2, like expanding that isn't too bad, but once you start getting in anything bigger than that, even like the 6, you'll see that it becomes a little tedious on that. Okay? But again, that's our first part of the objective, knowing when to add the exponents, but it's only when the bases are the same. And it's crucial to understand that when the bases are the same and they're being multiplied, the bases, just take the exponents and add them together. So we're going to do the same thing on this next one. I'm going to expand it again. So we got b to the power of 6. All right. First up here, so that's b, but it's 6 times multiplied. 1, 2, 3, 4, 5, 6. All being multiplied. And then we do have this multiplication here. So we're going to show that in between here in black. And then in orange, I'll put these other 2 b's being multiplied. So that's 1, 2 of those being multiplied. But again, we see that by expanding these, we ended with the same base, b. But how many b's do we have right here? Let's count them out. 1, 2, 3, 4, 5, 6, 7, 8 total b's being multiplied, all being multiplied. So that would be b then to the power of 8. But again, if we were to use this property, right, because that's part of our objective here is knowing when to add the exponents. Since the base b is just being multiplied in the original part, b to the power of 6 times b to the power of 2, we could have taken those 2 exponents of 6 and 2. And yeah, you can just add those together. And 6 plus 2 we see is the 8 right there. Yeah, so if you ever see that the bases were different, and that's a critical part of this property, is the bases need to be the same in order to start adding, or we'll see as well with subtraction of the exponents as well. Now, it's possible to have many bases, but it's possible to apply these. Sometimes they're just not right next to each other, which we'll see some examples like that as well. So this is the rule. And again, this when it's showing x right here, sometimes these can be numbers, sometimes they're letters, it doesn't really matter. But you're going to take these exponents, and when you're multiplying the same base, it has to be the same base, take the exponents, add them together. And again, this is a nice shortcut instead of having to expand these all the time, which you could do. But it's a nice shortcut to make this a little bit more convenient. All right, so here's 4 more examples for us. Looks pretty good. So we'll start with the 14 to the power of 23 times 4 to the power of 8. Now we do not want to solve these, we just want to simplify them. Okay, so that means that it's going to stay in exponential form. And And what I notice is that the bases are the same and that they're being multiplied, which means that the answer will have the same base. But what I'm then going to do is take the two exponents of 23 and 8, and I'm just going to add those together. Why am I adding them? Because it was multiplying these two same bases. And then this gives us a final answer, fully simplified. It's base 14, but 23 plus 8 is 31. So then we get 14 to the power of 31. Now it's going to work for this negative 72 also. So I see I've got the same base, negative 72, being multiplied. So I'm going to keep my same base, negative 72. It came in parentheses, so I'm going to keep those parentheses as well. But then I had exponents of 10 and 13. 10 and 13. And yeah, since we were multiplying this, the two bases, the same base, we're going to add those two exponents. All right? Then what we get, we're going to keep that negative 72 in parentheses, which is important when the bases are negative. But 10 plus 13 is 23. And then the same thing with the base 5s. Here I got base 5 and base 5, so my answer will be base 5, but I'm going to take those exponents of 94 and 78, and I'm just going to add these together. Well, let's go and add those together then. So I got my same base 5, but 94 plus 78 is a 172. So it's 5. It ends up being 5 to the power of 172. Very, very, very big number. And so in exponential form, it's a lot easier to deal with. Next up, though, we got a negative 3. And again, the negative, just like we know from the last lesson, negative bases should be in parentheses, which is shown here. I'm going to take my two exponents of 9 and 5, and since we are multiplying the two bases that are the same, we're going to add those two exponents. So I'm going to keep my negative 3 base here, but 9 plus 5 as my new exponent becomes 14. All right, and that is simplifying all four of these. And while I've shown the step in between, right, with showing the actual addition, it is common for students in the past, they'll just show the addition right here, or right here, for example, here, or here as well, which means they don't really necessarily need to show this step in between, but you're welcome to do it either way, whichever way works best for you. All right, now sometimes students get a little caught up by this, let A be a number. Don't worry about that garbage. In fact, you could, if you wanted to, just cross it out so it doesn't get so confusing. All we're looking to do is simplify these. So in the last 4 examples where the bases were numbers, just like we've seen before, it is possible for the base to be a letter or a variable. So right here where we've got a to the power of 23 times a to the power of 8, well, we can apply this property where we're just adding the exponent. So since it's the same base, I keep the answer with the base a, but now I've got exponents of 23 and 8, and since we're multiplying those bases, we're going to add the exponent here. Then this becomes base a, but 23 plus 8, 31. We're down here at the f's, same base f, take your exponents, 10 and 13, and yeah, since it's being multiplied here, we're just going to add those two exponents. So then what do we end up with? F, 10 plus 13, that's our exponent, that's 23. Same thing with the base b's, same base, so we're going to keep that same base b, but our two exponents of 94 and 78, since it's being multiplied, the base, we're going to add those two exponents. So simplifying, fully simplifying. Going to keep that base the same, but 94 plus 78 as the exponent, 172. So yeah, you may see this with just letters as your bases, and that's okay. All right, here's what we got to do on this one. We got to find the value of x that would make this a true statement. Now we see that the bases are all the same, -3 in parentheses, -3 in parentheses, and -3 in parentheses. Which means all we would really be doing is looking to apply this property. So that's 9x. Since those are the exponents of the two bases being multiplied, that means we'd have to add those together to get the exponent of the answer, which is 14. So you can apply principles of equality to solve this. Not everyone needs to, and that's okay, but that zeroes out the 9. Drop your x, 14 minus 9 is 5. So if you replace that x with 5, then you'd get -3 to the power of to the power of 9 times -3 to the power of 5. Yes, that would equal -3 to the power of 14, because you just take 9 plus 5 is 14. Well, what do you do if there's many of the bases? That's okay. Again, you could expand these if you'd like, but I think this property makes this just a little bit more convenient. So right here on this first example with base 9s, again, I see a base 9. It's being multiplied. So I'm going to keep the base 9 there. But my exponents, 4, 6, and 13, again, just listing these 4, 6, and 13. Since all of the base 9s are being multiplied, we can just add these, all three of these exponents together. So that's possible to happen, which is going to keep the base the same, but the exponent will change. 4 plus 6 plus 13 is 23 right there. And it'll work the same way, even though there's four bases. Again, since they're all the same, 2's, the 2 base, we're going to keep the 2 as our base. But we're going to take our exponents of 3, 5, 7, and 9, and we're going to add those together. So, keeping the base the same as base 2, 3 plus 5 plus 7 plus 9, I get 24. So just be aware, if you see many of the same bases, you may have to add more than 1 or 2 values at a time, like we've seen here. So what do we do if we got the same base being multiplied, but it's kind of far across from each other? That's not a problem. Just keep in mind that it just has to be multiplication throughout, right? Where we see multiply, 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 multiply. Same down here, okay? If for some reason there was a different operation between these, then we would have to treat this just a little different. But as of right now, we're just looking at multiplication. So it's okay to have 2 different bases, like we see here with base 6 and base 4. We can operate with these. Okay, so I look at my base 6, and for my base 6's, I see exponents of 5 and 14. Now again, they don't have to be right next to each other. As long as we know that all the factors are being multiplied, then we can take those 2 exponents of 5 and 14, and we're still able to add those together, even though they're not right next to each other. So we could apply the commutative property of multiplication to move them next to each other, but that's not necessary that we do that. So then this would result in an answer of base 6, but 5 plus 14 is 19. Okay, so that's just the base 6 part of this. So let's go to the base 4. Base 4 has exponents of 9 and 3. And again, those base 4s are still being multiplied. So I'm going to take the 9 and 3 exponents and add those together to get a new exponent for 4. 9 plus 3 is 12. Now since both of my bases are numbers, I'm going to show the multiplication between these. Now, if for some reason you wanted to write this in a different order, such as 4 to the power of 12 times 6 to the power of 19, that would be fine. That would still be for full credit right there, okay? So the order of these does not matter, just like we know the order does not matter with multiplication. And yeah, if you'd like to be technical, you can show the multiplication there as well. So let's go to the next problem then. We got base -4 and base 17. That's the only 2 bases I see. And the negative 4, again, it's important to know that that's going to be in parentheses, just as it shows. And then the base 17, you could put it in parentheses, but it's not necessary that you do. So let's go to base 4. I got exponents of 2 and 3 right there. So I'm going to take those two exponents, 2 and 3, and since those are being multiplied, everything is being multiplied, I'm going to add those two exponents, which would then result in negative 4 in parentheses, but 2 plus 3 gives us an exponent of 5. Next up, I got my base 17s, which have exponents of 5 and 7. So I'm going to show the work on that. 17 has exponents of 5 and 7. Just add those two together. So that's a new base 17 with a new exponent. 5 plus 7 is 12. Just kind of fit that in. Yeah, these are being multiplied. And again, I'm not going to write this second one down, but if you change the order as 17 to the power of 12 times negative 4 would still be okay. On this next problem, I have bases of 15 and also of 7. So I'm going to start with base 15, although you could start with base 7 if you'd like. But base 17 has exponents of 2, and then this other 15 has a phantom 1 exponent right there, okay? Which means that the two exponents, 2 and 1, I need to add those two together, which will then give me a new exponent for base 15, which is 2 plus 1 is 3. And then working with the base 7s, I've got exponents of 2 and 4. So I'll show that 2 and 4 as exponents of 7, but we're going to be adding those together because all of the bases are being multiplied. So for my new base 7, the new exponent would be 2 plus 4 is 6. And yeah, these are being multiplied. Then we found all the answers for these. So this is asking, how can we simplify this type of answer? We won't see anything like this on the assignment. In fact, you'll deal with this more in 9th grade than you will in this grade. So I'm just going to kind of breeze over this. So if you ever see that the bases are not the same, you should look to see if they can be changed to be the same. So when I looked at 3 to the power of 7, I would look at 9, and I would always be looking to scale that down. So if I can make 9 a base 3, which I can, that would be 3 to the power of 2. 9 is 3 times 3, so 3 to the power of 2. It allows us to then take those two exponents, 7 and 2, and just add those together. So then simplified, if we wanted this in exponential form, would be 3 to the power of 9. All right? And then you could look at this next one. Well, I got bases of 5 and 2. I can't really change these so that there's the same base. So this one would just be kind of fully simplified. Again, I'm just going to cross it out because we're not so worried about that right now. All right, it says let x be a number. Again, we're not so worried about this statement right here, but we do want to rewrite the expression in simpler form. So we would be looking to multiply any bases that are the same, right? Such as the 2 and 17. Those are just constant bases. Do keep in mind, though, when we look at 2 and 17 right here, this is a more common mistake than we wish happened, but like on this one, 2x to the power of 3, this exponent of 3 does not apply to the 2. Now, there are ways to make an exponent apply to more than 2 factors like this, or 2 bases, but this is not that case. The 2 has an exponent of, it's a phantom 1. Same with the 17, it has an exponent of phantom 1 right there, okay? So it's the same thing with this other factor here, x to the power of 7. The 7 does not apply to the 17, it does not apply, okay? So what that means is I can take 2 times 17 here, which is 34, and just say, well, I would then have 34. That would be simplified right there. But then we got the 2 base x's, which have exponents of 3 and 7 up here. So since we're multiplying these 2 bases, we're going to keep that base the same, but we're going to take the 2 exponents, 3 and 7, and we're just going to add those together. So then we get the same base, but x to the power, new power, 3 plus 7 is 10. So our final answer, 34 times x, but then with the power of 10. And yeah, you can show the multiplication between there if you'd like. I'm not going to though. This is how you would put this into the assignment as well. This is how it's going to want it. You don't have to put the x in there, but they'll have a box for the 10 and then a box for the 34. All right, so all of these have been examples of when we add the exponents. That's the first half of the objective. The next half of the objective is knowing when to subtract the exponents. Okay, so again, I've told you that we're going to be subtracting these exponents. So you know we're going to subtract these exponents, but again, I'm going to show you why it is that we are going to be subtracting these exponents, okay? So I'm going to start with this first example. It's 3 to the power of 5 all over 3 to the power of 2. So I do need a fraction line on this one. I'll do 3 to the power of 5 in the numerator. That's because it's in the numerator. So 1, 2, 3, 4, 5 threes right there being multiplied because it's an exponential form. And then the denominator, 3 to the power of 2. So in the denominator, 2 threes being multiplied. Now if we go back far enough, well, I guess the 7th grade anyways, we know that something divided by itself is 1. So in the past where you've seen teachers cross those out, they may have used the word cancel those out. It's not that they're being canceled so much as that it becomes then a phantom 1. So when I've crossed those out, I'm actually showing a 1 right there because it then becomes a phantom 1. But not only that one, but this one as well. Okay, so we end up with those 3's becoming phantom 1's. And then what do we end up with? Well, in the numerator, you had 3 times 3 times 3 right there, which could be fully simplified into just, well, 3. That's our base, and then there were 3 3's there. So 3 to the power of 3. Now that's expanding and then simplifying from there. But remember, part of this objective is that we can subtract the exponent. So we take this base 3 that we see in the original problem, right? Base 3 and base 3. So this is also important for using this property of subtracting the exponents. Again, the bases have to be the same in order to apply this property, okay? But what you're going to do is you're going to take the exponent of the numerator, which was a 5, and the exponent of the denominator, which was 3, and then they need to be subtracted in this order. Okay, it's always the numerator first, and then the denominator exponent second. And yeah, I put 3 there, I meant 2. It's supposed to be a 2 right there. 5 minus 2, yeah, that's this 3 right here, right? So it is possible just to subtract these. Now I'm going to keep expanding these examples just so you can see it, but on the future examples, we're just going to be using subtraction of the exponents. So on this next one, I got my big fraction line in the numerator. I got a to the power of 4, so there's 1, 2, 3, 4 a's. In the denominator, and yeah, these are all being multiplied, by the way, just to specify that. In the denominator, we got 3 a's all being multiplied. Well, from here, we see a divided by a is 1. It becomes a phantom 1. A divided by a is phantom 1. A divided by a is phantom 1. And remember, phantom values means that these can go away, or in other words, we can make them disappear. Okay, again, it's not necessarily that they're canceled, it's just that they become phantom 1's. So what do we end up with on this one? It's a, which is in the numerator. So it is okay to write your answer as a, but again, on the homework, you'd see a little box right here that you got to fill in. So what exponent goes in that box? Well, this is where the property comes in, the principle. So we're going to take the base a, and the 2 exponents we have there were 4. That's in the numerator, and then the exponent of the denominator base a was 3. Just going to subtract those out. Okay, so 4 minus 3, that would be 1 right there. So that's a to the power of 1, but just like we've shown without the box, it is possible to show this without, well, just making it a phantom 1. So it is possible for an exponent to be a phantom 1 like we've seen, but whether you show that or not doesn't really matter. But on the homework, again, if you see a box right there, you'd have to put the 1. All right, so let's expand this next one, which will work a little different, but I got b to the power of 3. That's going to be in my numerator. So I got 1, 2, 3 b's, all being multiplied. And then in the denominator, we got 5 b's. So there's 1, 2, 3, 4, and 5, all being multiplied. Okay, so again, we can make these phantom 1s by just checking these off. 1, 2, 3, anything divided by itself is a phantom 1 right there. Now, if we were to write this out as a full finalized answer, notice those 2 b's in green are in the denominator, so they actually need to stay there. And there's 2 of those, so I get b to the power of 2. The question then should become, well, what value would go in the numerator? That's where we need to see one of those phantom 1s. Okay, so this is writing this answer, but notice it has a positive exponent, which is okay. If we were to apply this property of being able to subtract the exponents, you take the b base, because it's a common base that's being divided, take the 2 exponents of 3 and 5, and of course, just like we've seen, you would then subtract these. Okay, well, that means that you'd have b to the power of 3 minus 5, that's negative 2. See that? So what this tells us is that 1 over b to the power of 2 is exactly the same as b to the power of negative 2. These are the same answer, but again, on the assignment, you're going to see that this would have some kind of box right here to put the negative 2. So it's important to know that it is possible to have negative exponents, but it just indicates that you're dealing with some type of fraction on this. So this is the rule. Again, it's important to know that the bases, they have to be the same, but when they are the same and you're using division or fraction lines like this, you just take the 2 exponents, whatever they are, and then subtract them, okay? So this is abstract because it's not showing these values, but these are going to be numbers here, and it's possible for the bases to be just letters as well. That's not a problem. All right, so let's get these done. And again, I'm just applying this property of subtracting the exponents. So when the bases are the same, like we see with the 7s, you're going to keep the base the same. But I take the exponent of the numerator, in this case 9, and then the exponent of the denominator, which is 6. And since we're using division here, I'm going to then subtract the exponents. So again, the base stays the same as 7, but simplifying 9 minus 6 then becomes 3. So 7 to the power of 3 would be our final simplified form of this. So same thing with this negative 5 base, and it is showing the negative 5 in parentheses, so I'm going to keep it there like this. But I take my 2 exponents, 16 and 7, and since we're using division here, we're going to be subtracting these 2 exponents. So then, my new final answer here, keep my base the same, and it's negative 5 in parentheses, which is important, but 16 minus 7 is now a new exponent of 9. Same thing on this next one, 13 to the power of 5 over 13 to the power of 4, so that's a base 13. It's the same base. And I take my 2 exponents, 5 and 4. Exponent of the numerator is 5. Exponent of the denominator is 4. And we're just going to subtract these because it's showing the division right here. So this gives me the same base of 13, but with the new exponent. 5 minus 4 is 1. And yes, again, it's still okay to show that as a phantom 1 if you'd like. I'm going to show the 1 here just because, again, on the homework, this would be some kind of box that you'd have to fill in. Now, keep in mind as well that I think there's a problem on the assignment where it doesn't show a box right here. in which case it'll say simplify this, but really all it wants would be the answer of 13 on this type of problem on the assignment, okay? So this one you would not show the exponent. If it does show you the base, then you're just typing in the exponent. If it doesn't show the base, then it just wants, well, whatever this value is. And yes, it is okay for bases to be fractions like this. We see the base of 8/5 in both the numerator and denominator. So we're going to keep that base 8/5, and we know from the last lesson that when bases are fractions, we should have the base fully in parentheses like this. So I'm going to take my two exponents of 9 and 2. 9 for the numerator, so that's my first exponent shown. 2 for the denominator, that's the second exponent shown. And since we are dividing here, we're going to be subtracting those two exponents. So we still end up with the same base of 8/5. We're just operating with the exponents right here. 9 minus 2 is 7. And yes, again, it's okay for bases to be letters. It's not a problem. We're going to keep the base the same because it's the same for both the numerator and denominator, x. But I take my two exponents of 5 and 4. 5 for the numerator, 4 for the denominator, and then subtract those because we're dealing with division of these bases. All right? So again, my answers still be the same base, but a new exponent, 5 minus 4 is 1. So this is another example, I think, where this could be in a box, and again, the answer there would just be 1. It's possible to have a 0 exponent as well, which keep that in mind, because I think there's an example like that on the assignment. So it is possible to have two different bases with division, just like we saw with multiplication, okay? So like this first example right here, with 3 to the power of 5 times 2 to the power of 8, all over 3 to the power of 2 times 2 to the power of 3. I know, and I can see that the two different bases I have are 3 and 2. Okay, so I just write out my two bases. And then for the 3, I had exponents of 5 and 2. 5 for the numerator, 2 for the denominator. And again, this order does matter. It will change if you get these mixed up. And since we are using division here, we need to subtract those two exponents. So that's just base 3's. For base 2, I got 8 and 3. 8 for the numerator, 3 for the denominator. Just subtract those two out, okay? And whatever I get from this subtraction will be the final answer that I get from this one. So base 3, base 2, and 3 got the exponent in red. 5 minus 2 is 3. And then the base 2 has an exponent in purple. 8 minus 3 is 5. Yes, these two values are being multiplied. And again, the order doesn't matter. If you did 2 to the power of 5 times 3 to the power of 3, that's okay. So what about this next example? Well, again, I see two different bases. -2 base and then a 95 base. And all I need to do, since we are using division on these, is take the two exponents and then subtract them. So for -2 base, I have exponents of 7 and 5. 7 for the numerator, 5 for the denominator, so the exponent then becomes 7 minus 5. For 95, we have exponents of 5 and 4. 5 for the numerator, 4 for the denominator. Make sure you subtract those as well. So these are being multiplied. But simplifying this fully, I get the -2 base and the 95 base, but with new exponents. -2 base has an exponent of 7 minus 5, which is 2. And the 95 base has a new exponent of 5 minus 4, which is 1. And again, these are being multiplied. So those are the two answers we get from this. This one and this one. And again, if the order was different for you, that's okay. All right, so for this stuff, again, it's possible to change the bases, just throw it away. And so 27, could we change the 27? We always look to the bigger number to see if it can be switched. So we'll keep 3 to the power of 23. But the 27, could it be a base 3? And yeah, that could. That's 3 times 3, which is 9, times 3 is 27. So that's 3 to the power of 3. So you end up with the same base of 3, but you take the two exponents, 23 for the numerator, 3 for the denominator, and just subtract those out. and we end up with the base 3, but 23 minus 3 is 20. And this would be the simplified answer that it's looking for. Again, you shouldn't see anything like this on the assignment, but it's possible you may see something like this in the future. All right, for examples like this, you just want to simplify the expression. Now do keep in mind that if you see examples like this, that 3x to the power of 8, 3 times x to the power of 8, that's actually in a numerator right there. Now if we remember from fraction multiplication from 7th grade, all you're going to do is multiply the 2 numerators and then the 2 denominators. So that would be the same as taking 5 times 3 times x to the power of 8 all over x to the power of 3 times 1. But I'm going to make that a phantom 1 right here, okay? So then what do? Well, we can multiply those 2 constants, the 5 times 3, which is 15. And then we can take the base x with its 2 exponents, 8 for the numerator, and 3 for the denominator. And since it's being divided, we can subtract those. So this then would be 15 times x, but its new exponent, 8 minus 3, is 5. And this would be our answer for this one. And this is how you would type it into the assignment as well. So there's going to be a box for the 15. It should show you the x base, but again, it should have a box for the exponent, and that's where you type the 5 in right there. So it's the same thing with this next problem. Again, that negative 4x to the power of 6, that's a numerator. Okay, which means you can just take the 5 and the negative 4 and multiply those to get negative 20. And then I see an x in the numerator and denominator. So I'm going to keep that base x, but I'm going to take the exponents. The exponent for the numerator is 6, the exponent for the denominator is 3, and since we are dividing these, it'd be subtraction. Okay, so I am kind of skipping a step on this, but hopefully this makes sense, because the final answer here, still got the negative 20, but the base x has a new exponent. 6 minus 3 is 3. And so this is our final answer right here. Actually, that completes the lesson. So we saw this in 2 parts, and this is kind of the first time we've seen this rule. But again, if you have the same base in a fraction or in a division problem like this, just take the 2 exponents and subtract them. So m and p would be numbers usually. And then you just subtract those 2 exponents, and you have yourself a new exponent.